How exactly does an electric discharge start? What are the different types of discharges, and how are they different from each other? In this video, I will attempt to explain this, so let's dive in and find out more. Electric discharge is the release and transmission of electrons and/or ions that form a bridge between 2 points which are under the influence of an electric field, meaning one side has a different potential. Electric breakdown or dielectric breakdown is a process that occurs when an electrical insulating material subjected to a high voltage suddenly becomes an electrical conductor and electrical current flows through it. Electric breakdown refers to the uncontrolled current flow as a result of an excessive field strength in the area that the current flow is occurring. This will cause the electrons to accelerate and collide with other molecules or atoms with enough force to cause further electrons to become dislodged from the impacted molecule or atom. When this occurs, it will also cause a positive ion to be created from the collision. This ion will accelerate in the opposite direction to the electrons and head towards the negative charge of the electric field. If it should collide with anything along its path, such as the metal plate, the ion, being much heavier, will cause an impact that will dislodge further electrons from the weakly bound structure. This will result in an avalanche effect that is responsible for the uncontrolled current flow, where the system's impedance is the only limiting factor for the current flow. Everything can ultimately undergo electric breakdown. It is just a matter of applying enough electric force for a given material. Electric discharges can be split into roughly 3 regimes: dark discharges, glow discharges, and arc discharges. Each has very different characteristics. These all assume that there is a gas or material between the electrodes to allow ionization to occur. There is one special case called a vacuum arc which does not require this, which we will discuss at the end. Dark discharge. Before even applying a potential across 2 plates with a gas in between them, it is important to understand that even if this gas was a dielectric, some of the molecules are continuously being ionized by background radiation or cosmic rays. If we now apply a potential across this, it will cause the ions and electrons to migrate to their respective electrode. This will cause a very weak electric current. In dark discharge, the gas is partly ionized, but the ions do not have enough energy to cause collisions to create more ions. Recombination cannot occur, but current does flow, meaning that it is not visible. If we now increase the voltage, we will eventually start to provide the electrons with sufficient energy to initiate a corona discharge. When a gas is exposed to an electric field of sufficient magnitude, any free electrons will accelerate under its influence. These may then collide with the gas molecules and dislodge weakly bound electrons, producing a free electron and a positive gas-ion pair. This process is often visible and is called corona discharge. It is often seen as a bluish glow in the air adjacent to pointed metal conductors carrying high voltages and emits light by the same mechanism as a gas discharge lamp. Corona are often observed near sharp edges or points that have a voltage attributed to them. This means that they don't normally propagate over the entire electric field. Coronas can be positive or negative. This is determined by the polarity of the voltage on the electrode. The physics of positive and negative coronas are strikingly different. In a positive corona, all the electrons are attracted inwards towards the nearby positive electrode, and the ions are repelled outwards. In a negative corona, the ions are attracted inwards and the electrons are repelled outwards. The glow of the corona is caused by electrons recombining with positive ions to form neutral atoms. When electrons fall back to their original energy level, it releases a photon of light. At a certain distance from the electrode, the electric field becomes low enough that it no longer imparts enough energy to the electrons to ionize the atoms as they collide. This is the outer edge of the corona. Outside this, the ions move through the air or other dielectric gas without creating new ions. In other words, from here on in, it is a dark discharge. the outward moving ions are attracted to the opposite electrode. The avalanche mechanism does not release enough energy to heat the gas in the corona region to ionize it, as occurs in an electric arc or spark. Only a small number of gas molecules take part in the electron avalanches and are ionized. The rest of the surrounding gas is close to ambient temperature. This means that a corona creates a non-thermal plasma. A positive corona is often seen as glowing blue-white, though many of the emissions are in the ultraviolet. It generally appears a little smaller than the corresponding negative corona, owing to the lack of non-ionized plasma region between the inner and outer region. It has a much lower density of free electrons compared to a negative corona, but are concentrated close to the surface of the conductor, in a region of high potential gradient, whereas in a negative corona many electrons are in the outer, lower field areas. A negative corona often appears as tufts of the corona at sharp edges, the number of tufts altering with the strength of the field. Although the electron density is much higher compared to a positive corona, the energy is much lower due to it being in a region of low potential gradient. Ionized gases produced in a corona discharge are accelerated by the electric field, producing a movement of gas or electric wind. Streamers or brush discharge. A brush discharge or streamer discharge is an electrical disruptive discharge which is similar to a corona discharge. It occurs when an electrode has a high voltage applied to it which is surrounded by a dielectric material like air. It is characterized by multiple luminous writhing sparks which are plasma streamers composed of ionized molecules from the dielectric material. These streamers will spread out in a fan-like shape. Both corona and brush discharges are sometimes called one-electrode discharges, as they occur in the vicinity of a single electrode, and don't extend as far as the electrode carrying opposite polarity voltage in the circuit, which an electric arc would do. They occur when the electric field at one of the electrodes exceeds the dielectric strength of the dielectric surrounding it. Often this will be air which requires roughly 30 kV per centimetre. At that voltage, free electrons in the air are accelerated by the electric field to a high enough velocity that they knock other electrons from neutral atoms when they collide, creating ions and additional electrons which go on to ionize additional molecules in a cascade reaction. The electric field will be highest at sharp points, so discharges tend to start at those points. The reason the discharge has such a limited extent is that the electric field decreases as the distance from the electrode increases. Eventually this will drop below the value needed for ionization. If the electrode is too sharp, a corona discharge will usually occur instead of a brush discharge. Unlike a spark discharge, where a large percentage of the maximum possible stored energy is released per discharge, a much smaller percentage of the maximum energy is released per brush discharge. Associated with this type of discharge are an acoustic cracking and a burst of current. The energy density is larger than a corona discharge. When a conductive object is brought near a charged insulated object, a brush discharge can occur. The electric field to initiate a brush discharge can be generated by charge on the electrode or on a nearby insulating surface. Electric glow discharge is a plasma formed by the passage of an electric current through a gas. Often it is created by applying a voltage between two electrodes in a gas tube filled with a low pressure gas. When the voltage exceeds a value referred to as the striking voltage, the gas ionization becomes self-sustaining, and the tube glows with a coloured light. The colour of the light will depend on the gas used in the tube. Conduction in a gas requires charge carriers, which can be either electrons or ions. These will come from the ionization of the gas molecules in the tube. In terms of current flow, glow discharges falls between dark discharge and arc discharge. In a glow discharge, the electrons leaving the cathode have enough velocity to cause collisions which create a cascade effect. This means that for every electron leaving the cathode, at least one other is created in the process. Up until the breakdown voltage, there is little to no glow and the electric field is uniform. When the electric field increases enough to cause ionization, the glow discharge develops. At this point, the electric field is considerably modified by the presence of the positive ions, and the field is concentrated near the cathode. As the current increases, more of the cathode surface is involved in the glow. As the current steadily increases, it will eventually switch to an arc discharge. The regions of a glow discharge. This can be divided up into a number of areas. The cathode layer. This begins with the Aston dark space and ends with the negative glow region. The cathode layer shortens with increased gas pressure. The cathode layer has a positive space charge and a strong electric field. The Aston dark space. Electrons leave the cathode with an energy of about 1 electron volt. This is not enough to ionize or excite atoms. This leaves a thin dark layer next to the cathode. Cathode glow. Electrons from the cathode eventually attain enough energy to excite atoms. These atoms quickly fall back to ground state, emitting light at a wavelength corresponding to the difference between the energy bands of the atoms. This glow is seen very near the cathode. The cathode dark space. As electrons from the cathode gain more energy, they tend to ionize rather than excite atoms. The opposing charges quickly separate and do not immediately recombine. This results in more ions and electrons, but no light. This area is also referred to as the cathode fall, as the largest voltage drop occurs in this region. Negative glow region. This region is the most intense on the cathode side and has a relatively low electric field. It is usually longer than the cathode glow, and the electrons carry almost the entire current in this region. Here, electrons that have been accelerated through the cathode region produce ionization and intense excitation, which causes the brightness in this region. The Faraday dark space. The energy from the electrons is slowly used up, meaning once they reach the Faraday dark space, their energy is low, and electron density decreases by recombination and diffusion to the walls in this region. The net space charge is very low and actual electric field is relatively small. The positive column. This region is quasi-neutral. The electric field is small in this region and is just enough to maintain the required degree of ionization at the cathode end. It is generally a long uniform glow, but moving striations or ionization waves can be triggered spontaneously by a disturbance. Anode glow. The anode glow is a bright region which is slightly more intense than the positive column. This is the boundary of the anode sheath. The anode dark space. This is a region between the anode glow and the anode itself. It is the anode sheath which has a negative space charge due to the electrons travelling from the positive column. The anode will pull electrons out of the positive column. Electric arc or spark discharge. An electric arc is an electrical breakdown of a gas that produces a prolonged electrical discharge. The current through a normal non-conductive medium such as air will produce a plasma. This plasma may in turn produce visible light. An arc discharge is characterized by a lower voltage than a glow discharge and relies on thermionic emissions of electrons from the electrodes supporting the arc. An electric arc is the form of an electric discharge with the highest current density. The maximum current through an arc is limited only by the external circuit, not by the arc itself. An arc between two electrodes can be initiated by ionization and glow discharge when the current through the electrodes is increased. The breakdown voltage of the electrode gap is a combined function of the pressure, distance between the electrodes, and the type of gas surrounding the electrodes. When an arc starts, its terminal voltage is much less than a glow discharge, and the current is higher. An arc in gases near atmospheric pressure is characterized by visible light emissions, high current density, and high temperature. An arc discharge is distinguished from a glow discharge partly due to the fact that it has a similar temperature for the electrons and positive ions, whereas in a glow discharge the ions are much colder than the electrons. A drawn arc can be initiated by two electrodes initially in contact and drawn apart. This can initiate an arc without the high voltage glow discharge. Electrical resistance along the continuous electric arc creates heat, which ionizes more gas molecules, gradually turning it into a thermal plasma. In a thermal plasma, the molecules, ions and electrons are all at the same temperature. The energy given to the electrons is dispersed rapidly to the heavier particles by elastic collisions. The resulting plasma is so hot it is capable of melting and vaporizing most materials. The current in the arc is sustained by thermionic emissions and field emissions of the electrons at the cathode. The current may be concentrated in a very small hot spot on the cathode. Current densities of around 1 million amps per square centimetre can exist. An electric arc is a continuous discharge, while the similar electric spark discharge is momentary. It can occur due to a direct current or an alternating current. In an AC discharge, the arc may restrike on each half cycle. Once the arc is established, increased current results in a lower voltage between the arc terminals. This property is the reason uncontrolled electrical arcs can become so destructive, since once initiated, an arc will draw more and more current from a fixed voltage supply until the supply device is destroyed. Leader spark discharge. A leader is a hot, highly conductive channel of plasma that plays a critical part during dielectric breakdown within a long electric spark. When a gas is subject to a high voltage stress, the electrical field is often non-uniform near one or both of the high voltage electrodes. Breakdown initially begins with the formation of corona discharge near the electrode with the highest electrical stress. If the electric field is increased, longer length cold discharges, called streamers or burst corona, sporadically form near the stressed electrode. The streamers attract multiple electron avalanches into single channels, propagating forward quickly via photon emissions, which lead to photoelectrons producing new avalanches. The streamers redistribute charge within the surrounding gas, temporarily forming regions of excess charge in the regions surrounding the discharges. If the electric field is strong enough, the individual currents from multitudes of streamers combine and create a hot, highly conductive path that projects from the electrodes. The projected channel of the hot plasma is called a leader, and it can have an electrical conductivity approaching that of an electric arc. The leader effectively projects the electric field from the nearby electrode further into the gap. The tip of the conductive leader now forms a new region from which streamers can extend even further into the space between the electrodes. As new streamers feed the tip of the leader, the current supplied helps keep the leaders hot and conductive. The larger the voltage, the further the streamer is able to project, progressing in a series of jumps until it is able to bridge the gap between the electrodes. Although leaders are most often associated with the initial formative stages of a lightning stroke, they are characteristic of the development of all long sparks. Partial discharge. A partial discharge is a localized dielectric breakdown of a small portion of a solid or fluid electrical insulating system under high voltage stress, which does not bridge the space between the two conductors. A partial discharge usually occurs in voids located within the material and is usually non-sustaining. Alternatively, it can be described as a transitory discharge mechanism that can occur in voids in dielectric material or between the conductors across the dielectric material, which provide electric field stress between the two conductors. Partial discharges require an electric field for the plasma to propagate, so once the plasma has bridged the gap, the electric field collapses, resulting in the plasma dispersing, and the whole partial discharge process would need to start over. A partial discharge is not visible as it occurs inside a dielectric material. The effect of altitude or pressure on breakdown. As plasma formation comprises accelerating electrons in an electric field, then the less collisions that the electrons have to make with the gas molecules, coupled with the fact that the accelerated electrons will achieve a much higher velocity, means that a low electric field will be required to create a partial discharge. Louis Carl Friedrich Paschen was a German physicist known for his work on electric discharges. In particular, he was able to verify experimentally that the voltage required for a partial discharge to be observed was directly related to the product of both the air pressure and the distance of the air gap. The graph from this experiment looks as follows. In order to understand the graph, we have to assume that a test setup is at sea level. This corresponds to the far right-hand side of the graph. As we increase altitude, the pressure will drop, and we move to the left and see that the voltage required to break down decreases. The lowest point of the graph is known as the Paschen minimum. Any further increase in altitude now requires a rise in voltage for the electric discharge to be observed. The accepted reason for this is that these extremely low pressures are now creating a vacuum where there are no air molecules capable of transporting the plasma or being ionized. Any observed discharges beyond this point are likely due to other phenomena such as vacuum arc discharges. Vacuum arcs can arise when the surface of a metal electrode in contact with a good vacuum begins to emit electrons, either through heating or in an electric field that is sufficient to cause the electrons to be ripped away from the surface in a process called field electron emission. Once initiated, vacuum arcs can persist. As the freed electrons gain kinetic energy from the electric field, they will heat the metal surface through high-speed collisions. This process can create an incandescent cathode spot, which frees more particles, thereby sustaining the arc. At sufficiently high currents, an incandescent anode spot may also be formed. A thermionic vacuum arc can be ignited in high vacuum conditions between a heated cathode and an anode. The accelerated electron beam incident on the anode heats the anode to a high temperature. After establishing a steady-state density of the evaporating anode material atoms, and the voltage applied is high enough, a bright discharge is ignited between the electrodes. And that brings us to the end of this video. I hope you found this useful. If you did, I would really appreciate a thumbs up, and please consider subscribing if you are interested in more of this type of content. If you'd like to support this channel, you can via Patreon, Super Thanks on YouTube and PayPal. And if you are interested in merchandise, I will leave a link in the description below. As always, be brave, be curious, the truth is waiting for us. Until next time.